Okay, let's unpack this. Imagine a technology where sound waves, actual sound, can precisely manipulate laser beams. I mean, it sounds like something straight out of science fiction, right?
Sure.
But it's not only very real, it's quietly driving innovation across just an astonishing number of fields.
It really is.
So today, we're doing a deep dive into the fascinating world of acousto-optic modulators, or AOMs as they're known. Our mission really is to demystify what these AOMs are, explore where they're making a significant impact, understand the forces shaping their market, and maybe peek into what the future holds for them. And this is all based on a recent market analysis you shared.
Right. And what's truly fascinating here is the elegant simplicity, almost, of how these devices actually work. At its core, an AOM really harnesses the power of this acoustic-optic interaction. So think of it this way. You introduce sound waves, usually at ultrasonic frequencies, into a transparent material.
Okay.
These sound waves create a periodic variation in the material's refractive index. Essentially, they're forming a temporary dynamic diffraction grating for light.
So it's almost like the sound wave itself is creating these tiny little oscillating lenses inside the material.
Precisely. Yeah, that's a great way to put it. And the materials, well, they're crucial. We're talking about things like lithium niobate, tellurium dioxide, or quartz. They're specifically chosen for their high acoustic velocity and, importantly, their transparency to the laser wavelengths being used.
Right, that makes sense.
And it's this really precise interaction that allows AOMs to modulate a laser beam's intensity or its frequency or even its direction with, incredible accuracy.
Wow. That's a pretty foundational piece of technology then. So what does this foundational tech actually mean for the real world? Because this isn't just some lab curiosity, is it?
Not at all.
We're looking at a market that was estimated at, what, approximately $300 million US in 2023?
That's right, around 300 million.
And it's projected to skyrocket, basically, to USD 520 million by 2032. That gives it an impressive compound annual growth rate, a CDRR of about 8.5%. That feels significant.
Oh, it absolutely is significant. And the primary drivers for this growth, they're pretty clear. It's really the surging demand for sophisticated laser systems across just really diverse industries. If we kind of connect this to the bigger picture, AOMs are becoming absolutely crucial. I mean, indispensable, really, for the expanding use of lasers and everything from advanced scientific research and precise material processing to life-saving medical diagnostics.
Okay, can you give us maybe a concrete example of that real-world impact?
Certainly, yeah. Take August 2022, for instance. There was a case where AMS technologies used an acousto-optic device to significantly enhance biological tissue visibility. Now, that's a truly significant discovery for healthcare research. It could potentially lead to, much better diagnostic tools down the line.
That's fascinating. Yep.
And if we look at the regional landscape, North America currently holds the largest market share. It was about 35% in 2023. And this is largely driven, as you might expect, by its sophisticated tech infrastructure and extensive R&D investments. Europe follows pretty closely behind at about 30%, thanks mainly to its robust industrial and research applications.
Okay, so North America and Europe are leading, but what about the rest of the world? I mean, I'm curious where the next big surge might actually be coming from.
Yeah, that's a great question, because here's where it gets particularly interesting, I think. Asia Pacific is, well, it's rapidly accelerating. They held about 25% in 2023, but they're projected to increase that share to 28% by 2024. And importantly, they're showing the highest Kira GR around 10%.
Wow, 10%.
Yeah. And this rapid growth, it isn't just random. It seems to be fueled by accelerated industrialization and the increasing adoption of advanced laser technologies, particularly in manufacturing and healthcare across the entire region. So this really points to a potentially significant shift in where future innovation and, frankly, market leadership in laser tech might increasingly come from.
That is a substantial shift to watch. So, okay, with that kind of growth happening, who are the big players? Who's driving this in the competitive market?
Right. Well, we're talking about some prominent organizations. Gooch and Housco PLC, for instance, held a dominant 18% market share in 2023.
18%, okay.
Then you've got Isomet Corporation at around 15% and Brimrose Corporation holding about 12%. Their strategies seem pretty consistent across the board. Significant investment in R&D, naturally, but also mergers, acquisitions, and strategic partnerships to broaden their reach and their technological capabilities.
Makes sense. Now, how do AOMs actually stack up against other modulation technologies? I'm thinking of things like electro-optic modulators, EOMs, and maybe liquid crystal modulators, LCMs. Just maybe for our listeners who might be less familiar, EOMs use electric fields, right, to alter a material's refractive
Oh,
index.
that's correct.
And LCMs leverage voltage to change the orientation of liquid crystals for modulation. So how do AOMs compare?
Yeah, that's a really critical comparison. AOMs truly shine in certain areas. They tend to offer superior diffraction efficiency, which is important, and also wider wavelength band compatibility. Now, while it's true that EOMs often have faster response times, they're quicker.
Right.
In 2023, AOMs held approximately 40% of the overall optical modulator market. Compare that to EOMs at about 30% and LCMs down at 20%.
So 40%, that's a pretty dominant share.
It is, and it isn't just about raw performance specs, you know. It really highlights the critical role AOMs play in applications where both precision and reliability are paramount, even if it means sometimes a slight trade-off in speed compared to EOMs. And what's more, this share is actually anticipated to grow slightly, maybe to 42% by 2024. And that's specifically driven by their use in high-precision applications like optical communication, laser-based manufacturing, and LiDAR.
LiDAR, yeah, that's huge right now. Okay, that's an impressive market position. But, every technology has its Achilles heel, doesn't it?
Always.
So this raises an important question, I think. What are the significant constraints? What's holding the AOM market back, potentially?
Absolutely, there are definitely challenges. One major one is their sensitivity to environmental conditions.
Okay.
Take temperature fluctuations, for example. Research suggests that just a 1 degree Celsius variation can alter the frequency shift by as much as 1 megahertz.
The megahertz,
Yeah.
just from 1 degree. Wow.
Exactly, and that significantly impacts system accuracy. So this isn't just some minor annoyance. It means AOM-based systems often need costly and, frankly, complex thermal management solutions. That drives up the overall system cost and complexity quite a bit.
So it's not just about getting the AOM itself right, but the whole climate control system you have to build around it.
Precisely. Then you've got vibrations, mechanical stresses from, even subtle vibrations can reduce the signal-to-noise ratio by up to 10 dB.
10 dB, okay.
Yeah, and it can introduce phase noise, which is particularly problematic in really precision environments like high-resolution imaging systems or sensitive scientific experiments.
Right.
And beyond those environmental factors, AOMs also have some inherent performance limitations. Their bandwidth, for instance, typically falls within the 50 to 200 megahertz range. Now, that's useful for many things, but it does limit applications that need broader modulation capabilities, like, say, some forms of high-speed data processing. And while their diffraction efficacy is pretty impressive, maybe 80–90%, that still results in, non-trivial power losses, which can definitely be an issue in power-sensitive applications.
Uh-huh.
And finally, perhaps most critically, is the cost barrier. The high cost of AOMs themselves significantly restricts their, let's say, widespread utilization. And that high cost isn't just about manufacturing scale, it's often tied to the purity needed for the specialized crystals and the ultra-precise fabrication techniques required. Those are just inherently expensive processes.
It almost sounds like these AOMs are a bit like high-maintenance rock stars, demanding perfect environmental conditions to perform their best.
That's one way to look at it. There's some truth to that.
But despite these challenges, the AOM market is clearly on the brink of some exciting technological advancements, isn't it?
It truly is, yes. We've seen just an incredible evolution over the years from, basic modulation devices early on to these incredibly high-performance systems we have today. And that's been driven by continuous enhancements in materials and design and integration.
Right.
If we look back, initial AOM development really began in the mid-20th century, and this was followed by the introduction of novel materials like lithium niobate and tellurium dioxide. These offered much better optical and acoustic properties, and that really pushed the boundaries of what was possible at the time.
And what about more recently? Are there any specific innovations that have caught your eye?
Oh, definitely. A great example is Coherent INC's introduction back in January 2023. They brought out a 905 nanometer continuous 3 electrodes edge-emitting laser specifically for commercial LiDARs.
Okay, LiDAR again.
Exactly. And this isn't just some incremental improvement. It's capable of outputs up to 100 watts, but in compact, durable packaging. So you're getting significant power output in a really small form factor, which is exactly what applications like autonomous vehicles need.
Yeah, that power density is key.
Absolutely. We're also seeing a very clear trend towards miniaturization, making things smaller, and greater integration into photonic circuits. That's absolutely crucial for creating more compact and efficient laser systems. And alongside that, we're seeing the advent of more sophisticated digital control systems, which offer improved precision and flexibility in how these AOMs operate.
That miniaturization and integration, that sounds like a real game changer, especially for mobile applications or anywhere space is tight.
It really is.
So looking ahead then, what are the key strategies? What are the pathways for overcoming these obstacles we talked about and unlocking even further potential for AOMs?
Yeah, excellent point. Well, first, I think advanced materials research and development is just crucial. We need to find or engineer materials that enhance efficiency, improve reliability, and make them more robust under varying conditions. Less sensitive, more efficient.
Right, tackling that environmental sensitivity head on.
Exactly. Secondly, investing deeply in miniaturization and that photonic integration we just mentioned, that's going to be key for meeting the ever-growing demand for compact, efficient laser systems. You mentioned space constraints, and that's precisely the challenge.
Okay. And beyond the hardware itself, are there other avenues for growth?
Absolutely. I think leveraging AI-driven solutions is emerging as a really powerful way to meet increasingly sophisticated consumer demands. It could allow for more adaptive and intelligent modulation schemes.
AI touching everything, it seems.
Pretty much. Then there's that persistent cost barrier we discussed. Manufacturers really need to aggressively explore more cost-effective production methods. Things like automated assembly, maybe even exploring 3D printing for certain components, and of course pursuing economies of scale wherever possible. That's essential to make AOMs more accessible.
Makes sense. Lowering the barrier to entry.
Right. And finally, I'd say partnerships and collaborations are essential. Sharing resources, sharing knowledge across companies and research institutions that can foster innovation and help reduce costs across the entire industry, really accelerating the whole field.
Okay, so we've taken quite a deep dive into this fascinating world of acousto-optic modulators. You've learned about how these devices cleverly use sound to control light.
Hmm.
We talked about their significant growth trajectory, looking to hit over $500 million by 2032. We've seen their crucial role in everything from medical imaging all the way to LiDAR. And we've also touched on the challenges they face, like that environmental sensitivity and the current cost.
Right. And this all begs, I think, a really compelling question for you, the listener. As laser technologies continue to push boundaries, think about areas like quantum computing, advanced sensing, autonomous vehicles. How might these ongoing advancements, especially the miniaturization of AOMs, unlock entirely new applications? Applications we can maybe barely imagine today, making these devices even more indispensable in our tech-driven future.